Hello, and welcome to our presentation about contention window optimization in IEEE 802.11ix networks with deep reinforcement learning. Let's begin with what exactly is the reinforcement learning. But first of all, we have to talk about what is the machine learning itself. There are two main families of machine learning algorithms, the supervised and unsupervised. The supervised is one of the most common. It can be viewed as a new paradigm of programming of sorts. We can use it, for example, when you have a problem that you want to solve using the regular algorithm, the regular programming, then you need a programmer that knows how to solve this problem, and he will share his knowledge with the computer via the medium of code. Machine learning, however, can be used even when you do not know what is the way of obtaining the correct result, but you have a lot of data that shows you how it should be done. So, for example, let's say that you want to write a program that recognizes how to whether a mole is just a mole or maybe it is a melanoma. If you were to do it using the regular programming, you would need a programmer that has some dermatological or oncological experience and is knowledgeable enough to do it on his own. However, in the case of machine learning, you only need a set of photos of the moles and information whether it is just a mole or whether this photo contains melanoma. Then, in the supervised machine learning paradigm, you can input the observation into the model. The model will output some prediction, whether, for example, it will say that a picture contains a regular mole, and if the model is wrong, and you know it because you know the correct result, which states, for example, that it is a melanoma, you can use your knowledge to correct the model, improving its performance. However, the takeaway in here is that the loss function, the difference between the predicted and the correct output, you need to be able to calculate it. The reinforcement learning takes it a step further. Because what if you do not know the correct answer, but you have some way of quantifying how good the answer that you are given is? So it is the very case if we are, for example, playing a game. So let's imagine that you are playing a game of Pong, in which there are two paddles. Each of one is controlled by one of the players, and the goal of each of the player is to bounce the ball in a way that scores you a goal, that moves it behind the line of your opponent's paddle. Now, for the sake of simplicity, let's say that it is only you playing Pong and you are playing against a bot. And in the terms of reinforcement learning, there are 5 things that we need to focus on. The first one is called the environment, and it is everything that is going on in the game, whether you see it or not. The second one is called the agent, and it is the player, it is you. The third one is observations or state, and those are the pixels that you see on the screen. Fourth, action, is the way of interaction between the player and the game. So in the Pong, it is either we can see it as either pressing the buttons or moving the paddle upwards or downwards. And finally, the reward is what you get for scoring or for losing a goal to your opponent. So in the reinforcement learning paradigm, which is the third of the main families of machine learning, we do not know the expected output because we do not know the correct move, but we have a way of quantifying how well the decision that we have just undertaken is. So, how can we use it in the Wi-Fi networks? One of the big problems in 802.11 networks is the CW optimization problem. Every time, or most of the times, when you want to transmit a packet, it has to undergo the same procedure. That is there to make sure that you do not interfere with any other transmission that is currently going on. So it can be separated into three phases. The first phase is called the delayed access, and in this phase we are listening to the medium to identify any ongoing transmission. If no transmission is going on right now, then you can go to the second phase, which is called the bug-off. In the bug-off, you draw a number from a range between 0 and the current CW value, and the number you draw will be the number of slots that you have to wait before sending the frame. If you have successfully waited out the necessary number of slots and no other station has started transmitting in this time, then you are free to go and you can start your transmission. If some other station was first because it drawed a lesser number, then you just have to wait for your turn, which will probably come next time. However, there's also a third option, in which you have selected, you have drawn a number that no other station have drawn lower than that, but there might be another station that has drawn the same number as you have. So you will both start the transmission at the same time thinking that you're clear to go, but a collision will still occur. An easy solution is to just raise the CW value, but the problem is that it is a trade-off, because while it is true that increasing the CW value means that the collision rate will go down, the problem is that with increased CW, there is a chance that the stations will wait much longer than they actually have to, which will drastically reduce our maximal throughput. So now that we have a problem and we know how we want to solve it, we need to frame the problem in a way that our approach can help. In the reinforcement learning world, it is called modeling the problem as a Markov decision process. And it basically boils down to selecting those 5 points of focus that we have talked about before. The first one is the agent, environment, and so on. So the agent, of course, will be the access point, because it is the environment, of course, will be the network. Everything that is going on in the devices, whether we can see it or not. We have selected the access point to be the agent because it is the central point of every wireless network. The agent, the access point, will take actions basing on the observed collision rate, and the actions that it will choose from will be different values of the contention window value. The access point will try to optimize the CW in respect to the throughput. So to this end, we have proposed CCOD, a centralized contention window optimizations with deep reinforcement learning. CCOD sees the network controlled. CCOD sees the CW optimization problem solved by using the deep reinforcement learning agent that is located in the access point. While the devices in the network try to transmit their devices and sometimes fail, sometimes succeed, how many packets, how many frames they tried to send. Access point keeps track of how many frames it has processed since the last update, so it is able to calculate the collision probability. In CCOD, the collision probability is then sent to neural network for inference, which yields us the currently optimal CW value. The CW is then broadcasted and accepted in the other devices. The training architecture of CCOD is distributed between two parts. The first one is the network simulation, which is done in the NS3 network simulator. And the second one, the actual training of the agent, is done in Python runtime. The two parts are connected using the NS3 GIM interface. The training itself is divided into 15 rounds, each of them lasting for a simulated minute. The first 13 of the rounds are the ones in which the agent is actually training, and the last two are made for validation of the correctness of the algorithm. Both the scenario setting and the agent definition are easily customizable. To showcase this, we have trained the CCOD agent using two different reinforcement learning algorithms. The DQL, the Deep Q network, and DDPG, the Deep Deterministic Policy Gradient. CCOD's performance was evaluated in two topologies, the static and dynamic. In the first one, the number of the stations connected to the network didn't change over time. In the dynamic topology, the number of the station was steadily increasing from 5 up to the goal number. The first two graphs show how the mean network throughput changed with varying number of stations. The third one shows the momentarily throughput in the dynamic topology, in which the simulation starts with 5 stations and ends with 50. Take a note on how quickly the performance of the stock 802.11ax CW control mechanism deteriorates with the increasing number of stations. With 50 devices competing for the medium, the CCOD noted an improvement in throughput of over 40%. In the dynamic topology, in which new stations were joining every second, while the throughput of the standard 802.11 was going down with every new device, the CCOD was able to maintain the same throughput even though the number of stations were increasing. Thank you for your attention, and we hope that CCOD will be useful to your further research. The code for this that we have used for this publication is accessible on the GitHub, and the QR code on the slide will guide you to the repository.